Okay, let's start. It's a nice day today. I hope you're all having a nice day, and you have the energy to continue the class on neural networks. Let me first give you a recap on what we talked about last time. This microphone works? Okay, cool. So last time we started talking about neural networks. We talked about this architecture that we like to call multi-layer perceptron, feed-forward neural networks. This is how they look. There's an input layer. There are a bunch of intermediate layers, and there's output, right? So the way we talked about it is there's an input. It's vectorized. It's a collection of inputs given to us. We give it to the first layer of the network. Layer by layer, we calculate it, and until we get to the output of the network. This was what we called the forward propagation. And we talked about this training algorithm, which we called back propagation, which was a relatively simple algorithm, but maybe with too much details. But the high-level idea was simple. We basically calculate error of our prediction in the output layer, and we try to propagate it back to the previous layers using gradients and output the weights until our network starts to perform the way that we expected, right? That was the back propagation. And if you have understood at least the high-level idea of what we talked about, I should say, congratulations. This is one of the most important algorithms that you should know about in data science. And if you already feel that you know the high-level intuition about this algorithm, it's already a big progress, so be positive. And today what we are going to learn about is two variations of the architectures that we learned last time. Namely, we are going to learn about convolutional neural nets and recurrent neural networks, right? And before I get to any of these subjects, let me briefly mention something that we didn't have time last time. And that is the idea of pre-training neural nets. So most of what we talked about, it was supervised learning in the sense that there are a bunch of inputs and there are annotations, output labels for the given input. This is called supervised because someone has to annotate each instance that is given to us, right? This is what we call supervised learning. On the other hand, we know that lots of data that we have in the world, they're unsupervised. We have lots of text, we have lots of images without labels, right? How can we leverage these information? How can we leverage unsupervised data in order to improve our systems? And the idea is that the nature, although it might look very complicated, but there's so many patterns that result in intelligent behavior. For example, if you take images of nature, there are lots of patterns that are repeated all the time. For example, edges, curves, circular shapes, right? And in order to learn these patterns, I don't need to have supervised data. I can just look at the nature and learn something about it, right? And we want to encode this. We want to encode this intuition in a structure within our neural net, right? And that is what autoencoders are about, right? So the idea is that we don't have supervised data. We only have a bunch of inputs, right? And we want to find regularities, patterns in this data, right? So let's say this is my input layer. This is my input. And I want to pre-train my neural net. Let's say this is the first hidden layer of my neural net. If I force my neural net to predict, to first compress my input to a few hidden layers here, and then decompress it to the same dimension, to the same input that it got in the first layer, hopefully it's going to learn to find the regularities, the patterns in the input data, right? So this is my input. This is my hidden layer. It is smaller than my input. This input is often like, it can be 100-dimensional space. This hidden layer can be much smaller, let's say 10. And I expect my system to reconstruct what it gets in the input layer, right? This is what we call autoencoder because it wants to encode what it gets as the input, right? And this is the objective this is the loss that I'm going to try to minimize. The difference between the predicted output and what is given as the input, right? And these are the functions that get the input, transform it with a matrix multiplication. Maybe there's a nonlinearity here. It should be maybe ideally differentiable. We get the output of this, again, with decoder. We decode it and get a prediction, and we try to minimize their differences. And we try to minimize this objective over a collection of instances, let's say millions of sentences, right? And after doing this, so this optimization is being done over these parameters that are transforming my input, right? I'm updating these weights, and I'm learning patterns of my input. After doing this training, I can just ignore what I had here and only save this weight vector and do some form of supervised learning based upon the initialization that I've gotten here, right? And I can actually continue this a little bit more. I can stack a few more layers. Let's say my autoencoder gave me this pre-training for these weights. I can stack another, I can stack another layer here. This is what I did. So input, hidden layers, autoencoder, I drop this layer. I can repeat this again and stack another layer here, add decoder here, optimize it, again, drop that. And again, what this gives us is a good initialization to our initial weights of the neural net, right? This is our pre-training, and we can continue, we can add a supervised system on top of this and use it for a supervised learning problem, right? So this idea is called unsupervised pre-training. So just to recap it, what we have learned mostly is supervised learning. We had this architecture that wants to learn mapping from input to output. The weights are initialized randomly. So the problem here is that this architecture doesn't learn about regularities that exist in unsupervised data. On the other hand, what we talked about just now was a way to initialize parts of my network in an unsupervised way with lots of data, right? And in practice, we have seen that this improves the performance of a downstream supervised learning problem, right? We are not going to talk about this a lot. I just wanted to highlight it that this is an important technique, and it's an active area of research. But yeah, yes.
Is there any intuition behind why it improves supervised learning after doing it?
So intuitively, well, I have to repeat basically what I was trying to describe initially. So there are lots of patterns in unsupervised data, right? And this is cheap, it's free, right? Unsupervised data comes for free. And understanding the patterns of, let's say, sentences or natural images, it doesn't require anything directly related to the task, right? So if you understand how images actually look like, it's going to help any vision task. Did I answer your question? Sort of. Okay. Okay. We're going to get back to this idea towards the end of this lecture if you have more time. I'm going to try to complete it with more ideas. Okay, so we are going to continue. I'm going to move towards convolutional neural nets. And in order to motivate why these structures are important, I'm going to talk about this idea or concept that's called receptive field. Think about your brain. We have neural system. We make decisions. Our decisions are based on the inputs that we get from the nature, from the environment. For example, my eyes, I can look at you, right, and I can scan you and make some decisions and do something with that. What is interesting about this system is that sometimes I can focus, I can look at individuals, or I can make my horizon relatively wide and basically look at everything, a holistic view of what I see, right? So it is this ability to focus and unfocus that is really interesting about our system. Same thing about our auditory system, right? I can pay attention to some signal, or I can just listen. So the idea, and this is called receptive fields. The basic receptive field is what takes a signal from the nature and conveys it to our sensory information, to our neural system, right? And the question is, how can we actually replicate this in a computational way, right? Let's say probably most of you are seniors, and next year you're going to be working somewhere, maybe as a data scientist, and you have this manager who comes to you and says, all right, you have a degree from this Ivy League school, and maybe you can help us with design of this face recognition system, right? So we want you to help us to create this neural network system here, which takes in an image. It might contain a face, or maybe not, right? We want you to help us design this neural network, which tells us whether this image contains a face or not. That is the task. How is this related to the concept of receptive fields? The discussion is about this input. We want to feed this image into our neural net. And by image, I'm talking about the matrix. It's a matrix of, 2D matrix of intensities, right? So let's say we are talking about only black and white images. If you have colored images, you have 3 layers, red, blue, and green, for example. Let's say this is one matrix, and we want to feed it into a neural net. The question is, how do you think you're going to approach this problem? And I want us to brainstorm on this a little bit because I think it's important. Yes?
It's like you can sort of just like, in some recursive way or iterative, I'm not sure, scan particular sections of the image. And so like if you see that like a certain section contains what looks like, at least to us, like an eye, and then to the left of that contains something else that looks like an eye, and then below, in between those two, contains nose and other facial attributes. If it has all of those things, or fits that pattern, then you would be able to say with some degree of certainty that it's a face.
Would you pre-design those patterns?
So no, I guess you would expect that the neural network would be able to learn those on its own.
Mm-hmm. Let's say we have this issue that some images are big, some images are small. How would you deal with that?
I guess that would have to do with, how you extract the features, and also I don't know if you would make it so that somehow the neural net would be able to, I guess generalize, so that way, what's it called? So it's about relative positioning, or maybe you would need to train it on images of all the same size. So, whatever your smallest image is in the training set, you need to resize all the images to fit those dimensions.
Can you remind me your name?
Joel?
Joel. Do you have any other ideas in addition to what Joel said? Like any if you want to like criticize Joel's idea or like suggest or build upon that? Brainstorming. Yes?
I guess a really simple solution to the different sizes problem is just to
compress them, yeah. Compress them. How about spatial correlation? Like we know that so Joel suggested we can design patterns, let's say pattern for eyes, or a pattern for lips. But there's also a spatial correlation, right? So we know that eyes, they appear in certain position with respect to lips, right? It's often not upside down. It's like eyes on top of lips, There's that face has certain shape. Or how would you take care of that? So let's just start with a slightly, Joel had a great idea. I think he's very close to what I'm going to present here. And I'm going to start relatively stupid, like very, very bad idea, right? So let's say I start with a feedforward neural net, and let's say this is the input layer, and this is an image. I'm going to connect all the values of this matrix to every single unit that I have in the input layer. What is the problem with this? One problem is, well, I have a lot of edges. So let's say if my image has, if there are 100 by 100 pixels, I'm going to have 10,000 edges here. That's a lot, right? So not a good idea. On the other hand, if I'm just summing up these edges here, it feels like the spatial correlation between these pixels, they're disappearing. It's not clear whether like which pixel is on top of which pixel. So spatial correlation is lost. I can try to get closer to what Joel was saying, and I can try to cut this image into smaller, smaller sections, right? I can dissect this. And I can try to connect each section to each input unit, right? This is slightly better in the sense that I have less edges, better, easier computation. But even still within each section, I'm still losing a little bit of spatial correlation. And it is not clear how I'm going to be able to deal with change of size. Maybe, as Daniel suggested, maybe I can compress images and like try to pre-process the images. But what if an image is too big, and by compressing, I'm losing too much information? How to deal with that? I don't know. Yes?
Would you want these like different patches to overlap a little bit so that you can sort of see the
Great idea. I think, so he's saying that rather than having independent, isolated patches, why don't you make them overlapping so that you kind of capture the correlation between neighboring patches. We are gonna do something very similar to that. So basically, can you remind me your name? Jordan. So Jordan we are going to do what Jordan was saying, a combination of what Joel said and Jordan was saying. So basically, we are going to have these patches, but these patches are going to be overlapping. And each of these patches, each of these filters, they're going to encode a certain pattern. Right? So, and we haven't defined what those patterns are, but let's just call them filters. Right? These filters we are going to apply them one by one at each location on the image, and we are going to get the output and save it and give it to an input unit here, right? And this filtering operation, this is what we call convolution. Convolution is basically element-wise multiplication of two matrices. We superimpose two matrices, a filter and the pixels of the image. We sum the values, and the result is the result of convolution. So convolution, filter, in this lecture, I'm going to use all of them to refer to the same thing. Right? And in order to deal with this variable size issue, we are going to use this operation, which we will introduce later. It's called pooling. Pooling is basically compressing the values of one matrix into a smaller predetermined matrix. Right? So let's try to expand this and see first, what is a convolution? Convolution is basically applying a filter to an image, right? And we are going to learn this filter. But for now, just to demonstrate how this filter works, let's try to fix it. Let's try to fix this filter. So in this case, since we are talking about images, these are 2Ds, but you can extend this to 1 dimension or 3 dimension or other cases. So this is our filter, and I'm going to try to apply this filter on this image. This is a face, and in the output, if you look at it, it has sharpened the color changes, the borders. Right? The way I'm going to apply this, I'm going to superimpose this on this part of this image. I have 0 here. I have -1, 0, -1, 5, -1, 0, -1, 0. And I'm going to copy, I'm basically applying this on the values of the pixels here, and I'm multiplying these element-wise, and I'm summing them, and I get the value, and I put the value here, right? And I'm going to move this patch around every part of this image, and I'm going to get this as a resulting image, right? So this is how you apply convolution on an input image, right? So just to, again, repeat what I just said. So let's say that I have this filter. Filter is a matrix. It's usually smaller than your input. You're going to start applying this on your input image. You're going to continue doing this. And each time that you apply it, you get a value. You're going to get it and put it in the resulting matrix until you apply it on the whole image, and you get a resulting image, right? So what this filter does, filter extracts some form of patterns. It can be a pattern about edges. It can be patterns about where the circular image is, circular part of the, where the curves, where the circular parts of this, where the lines. The filter is filter is something that we are gonna learn. Right?
So each of the new elements in your matrix is basically the dot product between a bunch of the original elements and this like filtering.
Yes. Yeah, and filter, and we are gonna learn filter, right? And we are gonna learn the filter, and we are gonna visualize it and see that, oh, gee, filter actually learns some interesting patterns about the task. Right? So we have roughly defined what convolution is. Let's say you give me an input image, and this is my convolution layer. I have a filter here. If I apply my filter here, it's usually the case that I have a couple of filters. It's not one filter. I'm going to get a bunch of resulting images, right? This is my input image, a bunch of filters. Each time that I apply a filter, I get a resulting image. And if you have multiple channels for your input, let's say different colors of your image, you're going to get different images for each of these channels, right? And the next step after this is pooling layer. Pooling layer is the operation that takes in the result of convolution and gives you a fixed size matrix, right? So let's say this is the operation that gave me the result of convolution. I'm going to apply pooling, and this is going to give me a fixed size value or matrix, right? What is pooling? Pooling is actually a very simple operator. It can be a max function, it can be average function, or something like that. And the idea is that, going back to what Joel was saying, convolution is a filter. Convolution is going to tell you whether there is a certain pattern in your image or not. For example, if that pattern looks for edges, in the result of convolution, you're going to have high values if there's an edge. There won't be any big values if there is no edge, right? So what max pooling does, this function is, it tells you whether at some point this convolution filter has seen any edge when it was scanning or not, right? So that's the intuition. So the basic building block that we have here in this convolutional net is a convolution plus a pooling layer. We apply this filter, we make it smaller. Apply the filter, make it smaller. And we are gonna repeat these building blocks a couple of times. Stage 1, it has each of these. Stage 2, stage 3, you can stack more of them. And at the end of this, we have a bunch of matrices. They're smaller, but there are multiple of them with fixed sizes, and we can apply them to a fully connected layer, a feedforward net, which is what we learned last time, right? So this is what we had last time. Just to give an example of, this is, by the way, this structure that we are talking about, this is widely being used in industry. Like a lot of image recognition systems that you see, let's say in Facebook, they use an architecture similar to this, probably much bigger than this, right? But this is something that people actually use, although it might look very simplistic, but it is powerful, right? Just to show you a real example of this architecture in industry, one of the first examples of this was used for character recognition. Right? So there's an image which contains a character. Let's say when you're mailing something to an address, you want systems to detect what are those characters. And the input is this image. This is from a paper that was published in the 90s, which was one of the first successful applications of convolutional net to this task. We apply the convolutions. We get a bunch of resulting images. They're slightly smaller than the input image. Then we do pooling layer, or here they have labeled it as subsampling. Then again, another layer of convolution, pooling, and this is the fully connected layer, which is what we had last time. Right? And the person who introduced this structure is the manager of AI research in Facebook now. So, yeah. Okay, how do we train this structure? So this is what we have now, input image, stage 1, stage 2, stage 3. Each stage contains one convolution, one pooling, and then fully connected layer, and class output, right? How are we going to train this? The idea is very, very, yes?
Sorry, can you explain the size of the previous one? Like why it went from 32 to 28 to 14 to...
Why it is smaller?
Right, so like how exactly do you, like, what is the relationship there?
Okay, that's a good question. Okay. You should be able to determine, so what is the size of this? Okay, help me here. So what is the size of this image? Okay, what is the size of this image? And what's the size of this filter? And so based on the size differences that you see here, you should be able to determine what's the size of the filter that was used. Is that clear? Okay, cool. Okay. Okay. We were talking about training systems. So the idea is very similar to what we had last time. Two passes. Forward pass, which is when we make predictions. Given input, we calculate output. In the backward pass, we're going to use gradient to calculate the errors at each step and update our weights, right? So what I have in the output is this error per instance, or average over multiple instances. I know that I can calculate this gradient in the output. This is what we showed last time. And we also showed that I can actually use chain rule in order to calculate this error at each layer, namely in the input of my fully connected layer. And the rest is basically following the same pattern that we had last time, use chain rule in order to propagate it back to each state and update the weights. By the way, just to make sure that if in case it wasn't clear, what are the parameters that I want to learn for each of these stages? What is it that I want to update? Joel? Exactly, the filters. I want to learn the filters that best distinguish the patterns in my input, right? So I'm going to calculate the gradients in the input. You may ask, how are we going to calculate how the gradient from the output of pooling is going to pass through the pooling and go to the input of pooling? Pooling, if it is a maximum function, basically you only pass it to the element that was chosen as the maximum. You can do the math and verify it. So basically, if you have three variables, one was chosen as the maximum, and you want to propagate the gradient back to one of these variables, you propagate it to the one that was maximum. And then with this, you can calculate the gradients and update the weights for each of these layers. That was relatively hand-wavy, but I hope you get the idea that it's basically the chain rule, and the details maybe at this point are not very important as much. This is a result of a real example. This is a real example that shows how these filters at each step look like. The task is something about whether it's something along the line of whether this image has a car or not, if I remember correctly. The people who created this, they try to visualize the filters at each step. These are the convolution filters, stage 1, stage 2, stage 3. What is interesting here is that in the initial layers, the patterns are relatively general. As we move on closer to the output, things get slightly more granular and more detailed. And once in a while, you can also spot some patterns that are particular to cars. For example, circular shapes, like wheels, right? And so this should be very intuitive. This is basically what Joel was saying initially. We designed some filters to detect certain patterns, and that is how these systems work. Yes?
Yeah. So how do we update the filters?
That was what this slide was about. In case this wasn't clear, let me try to repeat it again. So the idea is similar to backpropagation. In backpropagation, we do a forward step, right? We use existing network to make a prediction. And if the output wasn't as good, there's going to be error, right? It won't be zero. We're going to use that error to propagate it back and update the parts of the system that were not good enough, right? So if the filters are not good, they're going to have bigger gradients, and we are going to update. Oh, it is the out. Say it again.
I mean, for the filter,
Filter is a parameter of the system, right? And when I'm doing the backpropagation, I'm going to calculate the gradient with respect to each of the weights in my filter. So I'm going to update my filters using the gradient of error with respect to these parameters. Okay, demo time. I want to show you a convolutional neural net. This is supposed to be hopefully a fun demo. Dan, can you help me? Can one of you guys also help me? Come. Can you come on this? Can you come on the stage?
Okay.
Oh, you two. I'm gonna stay here. Come. Yes. Come. Okay. So this is the convolutional net. It's using my camera. The task is recognizing 3 categories from each other. So, and the output is gonna be Daniel, my class. Then it's gonna be Daniel, what? How do you distinguish each other?
What do you mean?
Daniel 2.
Okay.
And what is your name?
Kathleen, Catheden.
Like this?
Yeah.
Cool. Okay. So you stay outside there. Okay. So I'm gonna, when I press on train green, it's gonna capture images of my face through my camera. And it's gonna do a few rounds of backpropagation and train the network that is running in my browser, right? So let's do it. So, cool. So it says 99% Daniel. Now let's try Daniel number 2. Cool. It recognizes Daniel number 2. Kathleen. Yeah, look at the camera. Cool. Now it says Kathleen. Now let's try.
Daniel 2.
Ooh.
Daniel.
Cool.
Daniel. Daniel 2. Daniel 2. Daniel 2.
Oh,
Kathleen.
wait, say.
Kathleen.
Go on, come back.
Daniel 2. Kathleen.
Cool. Right?
Kathleen.
Seems to think
Daniel 2.
when no one is there. So this is Daniel 2.
Daniel 2.
Yeah, we don't have any fourth class of like no one. But
Daniel 2.
Can we add another class where it's just
Daniel 2. Daniel 2.
that's here. But maybe another time we will add it.
Daniel.
Okay.
Daniel.
I'm gonna mute this because. Okay. All right. That was convolutional net, and you can see how easy that is. There is a JavaScript library that gives you everything that we learned here for free. Exactly the same thing, right? Backpropagation, bunch of convolutions, but a bunch of filters. And any hackathon, have these kind of ideas in your mind, you know, as data scientists, if you decide to do so. Okay, moving on. Well, convolutional nets, a bit of history. Convolutional nets, they actually have a long history. They were introduced maybe like about more than 2 decades ago. It's just, at the time, initially, we had no idea how we were gonna, you can still hear me? We had no idea how we were gonna train them. It took us a couple of years to realize that, oh geez, this backpropagation actually works and we can use it. So chain rule might look very easy at this point, but at the time it didn't look that trivial. And nowadays, people are using it and using it extensively, and they're using it in like much bigger systems. Like this is an actual system. It actually didn't fit like vertically, so I had to put it horizontally. It's a system by Google. It is used, I believe, for image recognition. And I think it's more than 50 and something layers. And you need so much computation for training this, but it works. It works, and they have managed to improve their results by a significant margin. And we talked about this layers and the importance of layers. Over the years, we have seen that the systems over the years, their performance is improving. This is the error. This is the error of systems on image recognition tasks. Their error since 2010 from 28% has decreased to 3%, 4%. This is 2015. It's probably much better than this now. And one of the things that we have seen that these systems over the past few years, it has their sizes has dramatically increased, right? So there's something about size of these neural nets that makes them very special in order to capture really complicated high-level phenomena, right? And we don't exactly understand why this works. There's a slight lag between our theoretical understanding and practice, but we are getting there. So there is something here to be aware of. Since we talked about importance of depth, yes?
I noticed for the slide, there was a huge increase in the number of layers, but kind of less of an increase in accuracy. Do you think there's some sort of like asymptotic limit beyond which like you add more layers and it doesn't help anything? Because it sounds kind of like some of the overfitting examples we've heard of before that, like, you know, adding more layers might not, or adding more features won't always automatically make it better. But in this case, it seems to do so.
There is so much debate as to, you mentioned overfitting. There's so much debate as to what is overfitting in this case. Depending on how you ask this question, they might say yes or no. There is indeed, they work better. We have seen this in practice, whether you call it overfitting or not. But whether this is getting towards the real AI that we would like maybe in 20 years or not. So whether it's that or not, that we are not sure, and a lot of people say that it is not. What these systems learn with lots of layer, with lots of parameters is kind of regularities that we see in lots of data. But this is very different from how humans learn things. Humans, you can show me a task visually with only one repetition, and I can learn. And it's not because I'm smart. Any of us can learn it. Even kids can learn it. But these systems, for the most trivial tasks, they need millions of images, right? So this is a very different paradigm from how humans learn. So I think there are two questions. Do they work? Yes, they do work better. Are they going to get to the AI that people like to talk about, like strong AI? I don't think so. But this is subject to debate. Did I answer your question? Okay. Okay. Okay, so we talked about lots of layers. Training neural nets with lots of layers is not trivial. It's very hard. And one of the things that makes it really, really hard is this phenomenon of vanishing or exploding gradients. What is vanishing and exploding gradients? The idea is that, okay, think about backpropagation. We calculate the gradients at each step. And if you remember, there were multiplicative terms that multiply these gradients between each layers. And the more we are closing, the closer we are to the input layer, there are more multiplicative terms. And when you see multiplication or powers, what is it that could concern you? Exactly. Numbers can be huge, or they can be very small, right? And that is the problem. So especially that our computers, they have limits. They have limited precision, right? So they can't represent two big numbers that are too big or too small. And that is basically what is causing the issue. So that is what's called vanishing or exploding gradients.
When was the last time that the gradients, like calculating them, are additive? Am I remembering the wrong detail, or?
Yeah, I think you're remembering the wrong details. But I can show you after the lecture. Okay. So basically, okay, let me remind you. So we had these deltas that we memorized. Each delta was multiplied by one term that we newly calculated in that layer, right? So in that way, if you look at it, it's only quadratic. But each delta itself was calculated based on a quadratic multiplication in the previous layer, right? And each time you keep adding these deltas, if you're multiplying these, like if you write them in one place, it's going to be exponential. But I can show you the details after the lecture. Let me show you, I'm going to show this empirical graph so that you can see how this happens in practice. Sorry about the color coding if it's not clear. This blue one corresponds to, so these curves are average, like absolute value of the gradients. The blue one corresponds to the first layer, second layer, third layer, and fourth layer. And this is the absolute value of the gradients. And this is logarithmic. So each time that you jump, let's say from here to here, it's, by an order, it is smaller. What we see here is that here, when you move on, when you transition from the fourth layer to the third layer, the absolute value of the gradients is smaller by an order of magnitude, right? And so like when you get to the first layer, basically gradients are so small in this case, or it could be very big, and that is a problem, right? How can we deal with this? We have like heuristics to deal with this. We don't have systematic issues at this point. One idea is to add connections between long-range, add direct connections between long-range units. So for example, in this Google network that I showed here, if you notice, there are a bunch of direct connections that bypass a bunch of units here, right? These are put here in order to deal with this issue of vanishing gradients. Another idea is to use other optimization techniques rather than just using purely gradient-based first-order optimization techniques. You might be able to use better optimization techniques that might be slower, but they're more accurate in the way they optimize things. They use like Hessians. Another idea is this is a very hacky solution. Clip the gradients. If they're too big or if they're too small, try to scale them or clip them so that they match what you want. But this requires so much engineering and so much tuning. Okay, practical tips. Let's say you design a neural net. Let's say you're just done with designing it. It's usually the case that programs have buggy, right? So all programmers know that the first time that you're running a program, they probably contain a bug, right? A good way to check this is actually using overfitting. Take very few instances. This is the only time that overfitting can be helpful. Take a few instances, run your system on those few instances. If it is overfitting those instances successfully, it's a good thing because it is able to actually fit the instances. The only time that overfitting can be helpful. If it is not able to overfit a few instances, there is a problem. Maybe your optimization is wrong. Maybe you're not calculating the gradients right. Maybe you're optimizing a wrong objective function. All of these can be part of the issue. And you can also, one thing that's cool about convolutional nets is that you can visualize your features and see whether they actually make sense compared to your task, right? So if I'm trying to create a system that does image recognition, I want to see features that are descriptive of human faces. And I don't want to see features that are correlated. Correlated features means that I have too much units and they're doing the same thing, right? Features should be very distinct. Ideally, they should be orthogonal, right? So if there's a feature for ear, I shouldn't have 10 filters that capture the ear, right? I should have a feature for ear, one for eyes, and so on, right? I talked about if you have issues mentioned here. One thing that I want to highlight is that you can, it might be the case that your neural net is not big enough for your task, and you can check it by looking at the performance balance between training data and test data. If your system is not even able to overfit your training data, it probably means that it doesn't have enough units. It's underfitting rather than overfitting, right? And if it is slow, have this in mind. Neural nets are the best. You can parallelize them. You can use GPUs and you can use in order to make them faster. So in the remaining time, I'm going to talk about this. Yes?
Going back to the convolutions, if you see that your filters are bad, either they're noisy or correlated, what can you change about the network?
If they're noisy, if they don't make sense, there are a couple of reasons. There can be a couple of reasons. One is you're not calculating the right gradients. Maybe you derived the wrong gradients. Maybe you're not optimizing for the right function. Just to make sure that I understood your question, you're saying that I look at my filters, and they just don't make sense, right? What can be the reason? That's the question. Either I'm not optimizing for the right function, or maybe my task is not learnable. Maybe my gradients are not correct. There must be a problem. See, like it's a little hard to give like a blank solution for this. Like saying that I have this patient, he has headache. What should I do? I can tell you what are the symptoms, but it's hard to pinpoint what exactly is the problem, right? Okay, we're going to talk in the remaining time. We are going to talk about a slightly different structure, slightly different neural net. And for that, I'm going to try to show you a different problem so that you realize why this structure might be important. Let's say this is our problem. Now, from images, we switch to natural language. Now we have sentences. This is a simple sentence. This is our sentence. And for each of these tokens, I'm going to assign a part of the speech tag for each of these tokens. Right? Now, what are the challenges? The one challenge is that different sentences have different length. And so I have to be able to, if I want to create a system that does this, I have to be able to create a system that takes care of different sentences with varying size. And I have correlation between these tokens in the sense that the label that I'm assigning for this is here, it is kind of dependent on what I'm assigning here and what I'm assigning here. So there is sort of correlation because that's how language it is, right? That should be obvious. So the question is, how do you think we can deal with these kind of problems? How can we create a system for this? Let's say it's the same manager that you had that asked you to create an image recognition system, now asks you to create a system for this. How would you deal with this? Joel, do you have any ideas?
Well, you want to be able to remember whatever is the previous input. So I guess, like if you're looking at the word is, whatever neuron is doing that or stage in the system, whatever, you would want it to also be taking into consideration some number of words that came before that word.
Exactly. So this is what we want. Let's try to unpack what Joel just said. I feel like you should teach this class. So let's try to unpack what Joel just said. He said, so we want a system that is able to remember something about the past. So we want a system to remember something about the past, take in the input, make a prediction, and while it's making prediction, we want to take or abstract a part of what we have already seen and pass it to the next step, right? So we have one single structure, but we are going to try to repeat this multiple times here next to each other, right? So again, let me repeat it. This is my input. This is my hidden state representation, and this is the output. I'm gonna use the structure. It's one structure. I'm going to use it multiple times. Right? So basically what we are saying, infinite use of finite structure. I take in one input. I make a prediction. I have a state representation. I'm going to pass it to the next step. I'm going to use the same structure to take in different input, make a prediction, pass on the state representation. And what creates correlation between these predictions is that I'm remembering the state representations from previous predictions, and I'm using it for all of these predictions, right? This is basically the intuition that Joel just said. Right? So, and that is what we are going to implement as recurrent neural networks. Right? So, what is a recurrent neural network? For this example, I'm gonna show you a simpler example of this. We are going to try to generalize this. Let's say for each word, I can represent it as a vector. I can create a hash map of words in language, and I can create, let's say, randomly initialize a vector representation for each of these words in a hash map. Right? Let's say these are my vector representations for inputs for words. I'm going to create a function that maps this input to a hidden state representation. And I'm going to also try to calculate the hidden representation and pass it on to basically the combination of my input and current hidden representation. I want to transform it and pass it on to form the hidden representation of the next step, right? And this is the same structure, one single system repeated multiple times, right? Finite structure repeated infinite many times, right? And this is one way of doing it, not necessarily the only way of doing it. Let's say the input is a hidden state representation. This is a vector. Let's say this vector here. And your input is xt here. I take in these two inputs here, xt and ht minus 1. I transform both of them with two matrices. These are the parameters that I'm going to learn. There's a nonlinearity, and I'm going to get the hidden representation of the next layer. And I'm going to learn this, and I'm going to repeat this. I'm going to keep using this repeatedly. Right? I haven't talked about making predictions, but this is how I take in the input, use it multiple times, and make predictions. Yeah.
So if this, like, each stage is dependent on the previous stage, how do you initialize the first one?
Great question. We usually initialize it like randomly. Sorry, I don't have a better solution. Okay, now let's make a prediction. I'm going to create a function which transforms my hidden latent representation and makes a prediction here, right? Right. So, and this is this is a very simple recurrent neural net to solve the task that we just talked about. Right. So, what is good about this? The good thing is that it can do prediction on sequences. I can assign labels for each token. It's going to deal with variable number of sentences, variable length. And what is bad about this is that it might forget about history. It might forget about context. And it's looking at only one part of the context. It's only looking at what comes before each word. It doesn't look at the other side, right? Later on, you can see that, or if we have time, we will see that you can make this bidirectional in the sense that you can have part of latent representation that encodes the right context and the other part that encodes the left context, your left. And just to give you the big picture, this is what we learned last time. This is a recurrent neural network. It's only goes, there's no cycle here. We get the input, hidden layer, output. There's no cycle here. What we are seeing here is that is a structure that has cycles, a bunch of units that start with a state, we initialize it somehow, and each time it makes a prediction, and we reuse it to make predictions for the next state. It has cycles. It's a DAG, right? So if and what we are doing in practice is that we take in this structure, we expand it over time. Let's say if you have the cycle here, this is just an abstraction of this. This is not how we build it in practice. In practice, this is what happens. So there is the prediction from, we can start with some form of initialization. We make prediction, the state representation of unit 1 is passed to number 2 passed to 1 to 2, and this is what's encoded in this cycle, right? This is what we created here. So there's input representation. The states are connected through this latent representation, and using these latent representations, we made a prediction. The problem was that it pays attention to only one side of the context. What we can do, or people like to do, is to create a context that is bidirectional. And this is what people call bidirectional recurrent neural net. And these structure, you might be surprised, this is a very simple structure. But this year, or the current state of the art, at least now, is mostly systems that are based on this, at least in natural language processing as of now. Okay. Are you tired? I can mention a little bit about unsupervised pre-training in 5 or 10 minutes. How are you feeling about that? Feeling good? Wait, you're a minority. Everybody. Feeling good? Okay. All right. Let's continue with this, because I think this is important. And a big part of unsupervised pre-training is what the field, what current machine learning is mostly excited about. And I think that's why your next 10 minutes is actually more important than the previous past hour. But we needed that in order to learn the structures, in order to get here. Unsupervised pre-training is basically what we started with. We want to be able to leverage unsupervised data in order to create good initializations, good representations for our data, right? So I have lots of text. How can I use it? Let's try to start with this example. Let's say there's the sentence here. He was locked up after he, ellipsis. What can you put here? Probably something bad, right? So maybe he stole some money or he did something bad, right? But how do you get this? How do you get this understanding? So the idea is that we want to encode this understanding in the models. We want the models to be able to read something about history, about nature, about background, and be able to say something about what makes sense to put it here, right? So let's try to model that in terms of RNN modeling. So let's say I have this RNN that reads something about context, and there's a latent representation here, and makes a prediction about what is it that's going to come next, right? So in this case, my inputs are going to be these words here, and I'm going to be able to make a prediction about what's going to come next, right? And in order to optimize this, so what I'm doing is I'm taking, this is not supervised, right? This is all unsupervised. I'm taking something from the context, transforming it with my RNN, making prediction about what is it next going to come in the sentence. This is completely unsupervised. And I can create a really big RNN for this to make this prediction task. And what is interesting is that later on, so remember that what are the parameters here? The parameters is, one part of the parameter is the parameters of the RNN, the functions that transform my inputs and create these representation and decide these vectors. The other part of representation is the vector representation for each words. Let's say I start with latent representation for my words. They're random. That's how I initialize it. But I keep training this system, this RNN, on unsupervised data, on lots of text. And as I'm training this, I update the vector representation of my words, right? The question is, at the end of my training, how do these representations going to look like? Right? And there's something interesting here. These are real examples. I try to visualize the vector representation of a few words, and let's notice the patterns. The relationship between king and queen, the arrow that connects them in this vector representation, is very similar to the vector representation between man and woman. The connection between walking and walked, the arrow, is very similar to swimming and swim. Another relationship, Spain is very close to Madrid. Turkey, very close to Ankara. China, very close to Beijing. Okay. So this is all unsupervised. There is no labeling here, right? So I used RNNs in order to create some form of vector representation that forms or represent some form of semantic information about how each of these symbols mean. Right? To computer, these symbols, they're a bunch of characters, right? They're bytes. They don't have any semantics. But we created a system that used all this unsupervised data, lots of raw text, in order to create semantics. Right? And that is what matters for NLP. We want to be able to create semantics and use it for problems. Right? So you can, so this is basically the idea. And there are many extensions of this that make a better job in using the context, better complexity, and they're very popular in NLP. And if you decide to do NLP, this is going to be the main theme of, at least this has been the main theme of the recent years in NLP research. Well, that's what I had to say in 5 minutes of your time. If you have questions, or if you just want to chat, I'm here. Next time, Dan is going to be here. Yay. See you later. Oh, depends what you want to do. Google is your friend.
Sorry?
Google is your friend. But if you have like specific questions or like specific topic, you can always either ask TAs or you can drop me an email too. Yeah, I think Google, like you can, there's so much content on this, right? So the only danger is that you might get lost in like the ocean of content. So the hardest part is like being able to like abstract what is important and go after that.
And like the small websites that you use in the class, like how helpful could they be? Like just to learn the concept?
What's
Like the one that you showed, like the...
Oh, the demo?
Yeah.
That was just a toy demo, which it was for fun. I'm like, oh yeah, I'll come in. Are you walking? Yeah. Wait for a minute. Wait, did I answer your question? Okay, cool. Yes.
Are you randomly just simply distribution or all zeros?
That's the only thing that I have to say.
Will we get into it at all?
No.
Sorry.
So the RMN, right, is unsupervised, right? So are you using each of your previous work to predict the next work, or like you check and then see if you're right? And then
Yeah.
how do you make so you have a sentence, you just like predict the next one?
Yeah, that was the objective. So we use the context to make a prediction about future. Then we have a server function. If you're late, you can use it. Okay.
I can answer. You don't have to go in detail.
Yeah. So there's this object function that optimizes how close was my prediction, and then if you have an error, to use back propagation to take my rate. Very simple back propagation because it's only one way. And then you just keep repeating this, and it's very powerful. Yes. People do all things on videos, people do audios. Yeah.
So like if you can learn, and let's say an artist, like songs, type of songs, would you be able to produce a new song based on that?
Yes. Well, maybe I should. You can create handwriting. Let's say you say, show me this handwriting. Let's say you create all handwriting with Barack Obama. You can create an RNN, right? That system. And if you give it to text, it's going to replicate
you remember Obama had this like, yeah, differences. People have created environments based on that because it's the same person, same frame, like, said like different codes. Like you write text, speech, text, and it produces speech along speech talking about what the.
Is it the same way Watson works? IBM Watson.
Oh, no.
What about Google Magenta? It's their like audio project for this similar kind of thing. It'll generate. It like uses. I don't know if it uses neural nets. So I was asking.
I haven't seen it, but.
Yeah, it's like their music generation using machine learning project.
Yeah.
Isn't it also context? You're trying to find the context and then try to like produce what context before was. So then so why would it not be the same with Watson? Because like that's also like try to understand what the sentence brings to a context and try to answer it. You know what I'm trying to say? Like, it's a question. Ask a question and find the context. I mean, we can walk through that.
The difference is the nature of the problem. Do you remember like any Watson questions?
I don't know any question, but like
That question answering system, right?
yeah, it's like, well, it was like a what was it? I don't remember. Like, it was like it was like a question. They would ask questions and then we would go from all the data we have on the internet, like try to learn. So before asking the question, they had a context of so many different things that is happening everywhere.
Yeah.
And then based on that question, try to find a correlation between words and between the context. It's like the way you show like assuming and assume have the same context or something. Or like Beijing and China have the same context, or like they're the same category. Try to find the question related to what context.
To be honest, I don't think we
no just like read it, wait for add-on turn the value, turn a string to a value, turn the array. Things in the array, objects, things in there.
For the milestone one presentation, do we have to be in person or is it just a video?
I prefer that it's in person, but if like you already have plans to leave.
Yeah, I mean, my family's going out of town. I don't know if I should.
Yeah, I mean, just in that case, have your group members present what you did.